Today we have a session on polarization observations with Alma. Our goal today is at the end of the session, we will be wearing the Alma polarization glasses that Katarina made for us here. Our tutors today come as usual from different European ARC nodes. We have Rosita Palladino from the Italian ARC node in Bologna, Tobia Carozzi from the Nordic ARC node in Sweden, Katarina Immer from Allegro in the Netherlands, and me myself, Carmen Toribio from the Nordic in Sweden. And today's tutorial will consist of two parts. The first part will be an introduction by Rosita Palladino to polarization observations with Alma. And next, Tobia will do a little hands-on exercise using the Alma archive and the Carta tool online. So without further ado, I would like to invite with a warm welcome to Rosita Palladino to start her presentation.
Okay, thank you, Carmen. Thank you, everybody, for joining. And this is a very basic introduction to polarization, in particular at millimeter wavelengths, so the polarization that we can observe with Alma. And the outline of the talk is the following. So we will have a first very basic definition of the polarization theory and the parameters that we are going to measure with Alma, and some basics on the operations at Alma in full polarization, and some introduction to the calibration that we are currently performing on Alma data. And then the final part will be dedicated on the physical mechanism that generate polarization in the universe, with a special focus on the one observable at millimeter frequencies. Before starting, and since I don't want to forget it, I would like to thank all these people listed here, from which I learned a lot about polarization, and many slides are inspired by their talk. So thanks to them. So let's start with the basic introduction. Just a reminder about the thing we are dealing with, which are electromagnetic waves, and they can thought of as propagating sets of vectors oscillating, and these are the electric and magnetic fields, which are orthogonal to each other. In these and the following two slides, I'm going to show this kind of plots where only one vector is represented, which is the electric field, but you can easily imagine the orthogonal magnetic one. To describe properly the electromagnetic wave, we need to also know the geometrical orientation of the oscillation, and this is the polarization. The normal light, the white light, the natural light, is unpolarized with vectors oscillating in every direction, so there is no preferential polarization. But in nature, there are some materials which are able to distinguish between the different polarization direction. And for instance, here there is a scheme of a linear polarizer, which allows to transmit one of the components of the fields and absorb the orthogonal one. So the output from an incoming unpolarized light, after the linear polarizer, the light will be linearly polarized. And the vector here, the red arrow, will describe a line in the plane orthogonal to the propagation direction. Analogously, we can do a more complicated system introducing a quarter wave plate, which transforms the linear polarization into circular. And in this case, the electric field vector will describe a circle in the perpendicular plane to the propagation direction. In nature, obviously, the polarized light is in between these two extremes, so it's a mixture between linear and circular polarization, and it can be described as an elliptically polarized light. And here it's one of the possible schematic view of the polarization, which is the polarization ellipse indeed. To describe the polarization state of the wave, we need some parameters, and here you can visualize them in terms of the ellipse that the vector is describing on the plane. So to identify unambiguously the ellipse, we need to know its size and its shape. So we need to know one of the axes, in this case the major axis A, the ratio between the two axes, which gives the ellipticity, the azimuth angle, which is the angle between the x axis of our system and the major axis of the ellipse, and this is the chi, the azimuth angle. And we need to know the sense of rotation, so clockwise or counterclockwise. The angle here, the azimuth angle, is also called electric vector position angle, EVPA, and it's generally indicated as chi. In the archive, you will find, since this is something that we measure with observation, you will find the image of this angle, which is called, for simplicity, simply A. A particular property of this angle is the fact that it has a symmetry of pi. So rotating the position angle, the EVPA of 180 degrees, you get the same exactly the same state of polarization, the exact same ellipse. And this is something you have to remember, these symmetry properties of the angle. So the parameterization most used to describe polarization is through the Stokes parameters, which are actually something that we measure with observations. And here this formula shows the case where full polarization is considered. The Stokes I is the total intensity, which includes polarized and unpolarized light. Stokes Q and U describe the linear polarization, and Stokes B the circular polarization. So what we actually measure with the radio telescope is the orthogonal components of either linear or circular polarization, which can be used to describe the state of the polarized light. In general, radio telescope use circular polarization polarized feed, while Alma uses linear feeds. This means that each antenna has two dipoles orthogonal to each other, which register coherently the two orthogonal polarization states, linear. And this will provide the information necessary to describe the polarization of the emission. Alma is also an interferometer, as you for sure know, and so what we actually do is combine the observation of couples of antennas. So from each antenna we have two outputs, X and Y, and we have to combine these signals. Alma offers different polarization mode of observation, and you are mostly familiar with the dual mode polarization, which is actually registering only the cross correlation between X and X and Y from the two antennas. And this is actually giving you only the possibility to obtain the Stokes I image only. So only half of the lenses that we are using as a logo. Instead, if we observe in full polarization mode, that gives us the possibility to register the full cross correlation possibilities. So we have also the cross sense YX and XY here. And from this cross correlation, we can determine the polarization properties of the source, so we can get this polarized intensity image, which otherwise we will not get. So this is to get only this kind of observation gives you the full information about the target, also in terms of polarization. If we were in an ideal world, it would be easy to go from the cross correlations output of the correlator to the Stokes parameters. And so we will get total intensity from Stokes I, circular polarization from Stokes V, and linear polarization from a combination of Q and U. And this would be a very simple formula. Actually, in a real world, this is not the case. We have to deal with the instruments which are not perfect, and especially feeds the feeds that I mentioned before are not perfect, and it can happen that part of the signal in the from the X feed leaks into the Y and vice versa. So there will be a spurious polarization, which is due to the instrument and not to the target, but we have to take care of this effect and calibrate for it. So we will use a special calibration when we observe in full polarization mode, and we will use some sources which have at least 2% linear polarization. But actually, these sources are highly variable, especially at millimeter wavelengths. And here you see an example of one of these calibrators. Here you see in the top panel the light curve of Stokes size, so of total intensity with time, and the polarized flux in the middle panel, and the EVPA variation in time in the lower panel. So as you can see, these sources are generally highly variable, so we cannot assume to know a priori any property about their status polarization properties. So actually, Alma, since 2012, is taking a survey of calibrators, registering all these properties in time, so we can have these light curves and we can compare the results from the observation with the closest in time value in these plots. And you can find many more sources in this website, from which and from this list, the calibrator for your observation, if you ask for observations in polarization, is selected by the observatory in order to have the best source suitable for the calibration of your data. So then the consequence of this variability is that we cannot make any assumption on the properties of the calibrators. We have to derive them. And we can actually do so because there is another instrumental effect which helps us in deriving and separating the target polarization, the calibrator polarization from the instrumental polarization. And this effect is due to the angle between the axis of the antenna mount and the source. When the antenna track the source, the axis of the feeds are seen as rotating from the sky. So what we actually see is a parallactic angle variation. Parallactic angle is connected to the declination of the source and the latitude of the observatory, and it is during an observation you would see something variating like this in time. So the intrinsic polarization of the calibrator is stable in time. What changes is instrumental polarization. So from the data, we can actually see a variation in the polarization measured, which is changing in time due to this parallactic angle variation. And this is an example of the polarization gain ratio. And I use the same color coding to just show you the different blocks of observation taken in different times, where you can see that the polarization measured from the data is actually variating in time. And from this kind of variation, we can make models and disentangle the instrumental polarization from the intrinsic polarization of the target, which in this case is the calibrator. And this is actually the basic concept behind the current calibration scheme. We do not make any assumption on the linear polarization of the calibrators. We only assume that the circular polarization is 0. And this assumption is actually reasonable, considering that many quasars have no circular polarization, but it's still an assumption that we make, and the calibration is based on that. You can find the calibration, the basic calibration that we do for Alma data in some papers, and this is the first one that it was published. And also there is a CASA guide, you can check if you are interested, on a quasar observation where the different steps of the calibration are described. So the only thing that we need to do in order to be able to calibrate the data is to observe long enough to see a reasonable amount of variation in the polarization. And so these observations need to cover at least 60 degrees in parallactic angle, which corresponds in time to something more or less like 3 hours of observation, which is still very long considering Alma high sensitivity, and this is a limitation that the observatory is trying to reduce, improving the calibration, but it's still working on it. The result of the calibration is the determination of this instrumental polarization, which is also sometimes called D-terms, and we determine them for each antenna, and it amounts to a few percent, as you can see here in the y-axis. I just zoomed on the numbers here. For one antenna, 1% is this level, and this is 3%. Few percent, less than 10% is acceptable for Alma. And as you can see, these D-terms are variable with frequency. After this calibration, when we apply it to the data, we get the final images. And this is the case for a calibrator, where we have on the left panel the image obtained with non-calibrated data, and on the right panels, the calibrated data. So for the different Stokes, you can see the difference produced by the application of the calibration. The Stokes I parameter doesn't change much, while Stokes Q and U clearly show the effect of the calibration on the images, which is much smooth and without and less noisy than the previous image. In Stokes V, you notice the effect of the calibration, because the Stokes V image should be uniformly noise, because we assume that the Stokes V of the calibrator is actually 0. So what we saw in the image before the calibration was due to the instrumental polarization, and we removed this effect with the calibration. One note that of caution that we want to make clear is that if you search for a source which is a polarization calibrator in the archive, you will find that the Stokes I of that source will be equal to 1, because the calibration, the polarization calibration process normalizes the Stokes I flux. So this is then with this calibration, we took care of the instrumental polarization. There is another effect due to the imperfection or reality of the instruments, which is due to the antenna and feed geometry. And this produces a beam polarization, which we could correct for if we knew perfectly the antenna patterns for each Stokes. So actually, we don't have yet very precise model for that correction, which would be like the primary beam correction, which we usually do for Stokes I. So off-axis errors in linear and circular polarization could still be evident. And this led to the decision to limit polarization observation to just the on-axis observation. The field of view for linear polarization is limited to 1/3 of the field of view, and for circular polarization to 1/10 of the field of view. Actually, since this cycle on, it is possible to observe in mosaicing mode, which mitigates this error but doesn't eliminate them. So just like take-home messages from this Alma operation introduction, you need to know that Alma polarization observation need to be longer than usual. There's a limitation in the field of view, and systematic calibration on axis uncertainties are of this order: 0.03% of Stokes I for linear polarization and 0.8% of Stokes I for circular polarization. please visit the technical handbook for other details on the observations with Alma. Then now we move to just briefly introduce the physical mechanism generating polarization. And obviously when you think about polarization, you think about magnetic fields, because some sources actually emit intrinsically polarized light, and the most common mechanism to produce this polarized light is synchrotron emission, which is usually observed at lower frequency with the VLA and with all the interferometers, but also at Alma frequencies, at the lowest frequencies, band 3, band 6, we can still observe synchrotron radiation. This is due to the spiraling of ultra-relativistic electrons around magnetic field lines. This produces linearly polarized light, and from the total intensity we can determine, making some assumption, the magnetic field strength. We have to keep in mind though that the emission we measure is actually a combination of magnetic field and electron density, so we have to make assumption in order to determine the strength from total intensity. From polarization observation we can determine the orientation of the magnetic field in the plane of the sky using the polarization angle, and the fraction of polarization gives us an idea of the uniformity of the magnetic field in the source. These are a few examples actually of the very early times of Alma observations. I apologize, I'm going to show some Alma data, but this is not at all a complete list of the possible results that you can find in the literature obtained with Alma. It's just a random selection that I made. These are the few examples of the initial observation, and in particular the central image shows the 3C286 target source, which has been used for the CASA guide, and it's one of the very first observation taken during the science verification phase. It's a quasar, highly polarized, and you can see in the image the vectors describing the magnetic field direction. The left panel shows the hotspot of a radio galaxy, where from the magnetic field orientation it has been possible to infer that there are shocks undergoing in this ongoing in this region. And on the right panel instead we have a source which is usually known to be a strong calibrator. Actually, when you observe it at high resolution, you see a very nice extended emission, and it is also polarized. But obviously, you have heard about the most recent result from the EHT collaboration, which adds to the very nice image of the black hole in M87, also the polarization information. And here you see different images. The top one shows the Alma only image at 230 gigahertz. Here again we see synchrotron emission. This is the jet at the center of M87 observed with Alma, and there are the lines describing the magnetic field orientation. Then we go zooming in, and we get to the black hole magnetic field distribution when combining Alma data with the full millimetric VLBI network observatories. So another interesting effect that can happen to polarized light is the Faraday rotation, which is actually an effect that the linearly polarized electromagnetic waves going through a magnetic plasma have their electric vector position angle rotated by the presence of magnetic field, and you can see there's a linear relation with the lambda square, and this quantity, the rotation measure, is proportional to the magnetic field integrated along the dimension of the magnetized plasma crossed. So from this observation, you can get the magnetic field along the line of sight. And this effect is well observed, mostly at low frequencies, but also now it's possible to do some kind of this kind of studies also with Alma. And on the right panel, you see a recent result obtained with Alma data. On the left part, I wanted to show a result which is not from Alma, these are ATCA data, but I found them really instructive in terms of the Q and U variation with the lambda square that you see here in the top left panel. The chi variation is linear as expected, and here you see this plot on the right, the U versus Q Stokes variation due to the rotation measure, and you're going to see how it's easy to check the presence of rotation measure in the archive during the hands-on session. Then we move to shorter wavelengths, so the ones covered with Alma, millimetric and sub-millimetric wavelengths, where we have the dust polarization mostly. The dust grains align their minor axis with the magnetic field, and so with different wavelengths we can sample different grain size. And it's really interesting that from polarization we can obtain both information on the magnetic field and on the dust properties and dimension. The polarization observation at the frequencies determine the orientation of the field in the sky plane. To get the strength of the field, we need to apply some assumption, and there is this statistical method which has been developed in the 50s, which is called Davis-Chandrasekhar-Fermi method, where many assumptions connect the magnetic field strength to the turbulence of the gas. There's a lot of assumptions, so it is not possible to apply this method to all the sources, but it's mostly used in local universe, in the local galactic objects. Here are again some examples of dust polarization magnetic fields measurements obtained with Alma at the beginning of polarization observations. You see a different galactic object mostly. This is a circumstellar disk, hot core, and a star-forming region where you can trace the magnetic field through the dust polarization. The most right panel here is the very first result of dust polarization observation with Alma in a nearby galaxy. Actually, this is NGC 1068, and this is one of the fields where Alma may in the future make a big contribution, because it's the first time that we have enough sensitivity and enough resolution to be able to measure polarization at the scale of geomolecular clouds in nearby galaxies. Then Alma also, at the very beginning of its observation, revealed also the possibility that polarized emission at this wavelength is not only due to magnetic field, but also to the self-scattering of radiation from the same dust grains producing that emission, which are the sides of comparable to the wavelength of the observation. And that has been an amazing result obtained with many, especially in protoplanetary disks. And these are the very first detection of scattering from protoplanetary disk. And the way to distinguish between the polarization due to scattering and the one due to magnetic field is that the orientation of the field of the polarization changes with the frequency. And it has been shown that it's a common effect in protoplanetary disk especially, but it's still very interesting and giving a very important information about the dust in the protoplanetary disks. Now we move to spectral lines observation. I probably didn't mention that all these other effects are detected in continuum mode, so averaging all the frequencies. Now we are going to focus on spectral lines observation, and the most famous effect is the Zeeman effect, which is due to the presence of magnetic fields, some molecules, they have to have special magnetic properties. They can show the transition levels can be splitted in sublevels, and the distance between the sublevels is proportional to the magnetic field strength. So if we observe parallel to the magnetic field, we see circular polarization. And if we observe orthogonally to the magnetic field, we see linear polarization. So in the ideal case where a strong magnetic field is present, we could see both circular and linear polarization. And this is the full Zeeman splitting that we would expect from a strong magnetic field. And this is the signature that we would see in Stokes V, the circular polarization, and in Stokes Q and U for the linear components. But actually in real observation, it's really difficult to observe a linear Zeeman effect. The typically Zeeman effect is observed in circular polarization, and this is one of the famous results observed in Zeeman effect from the CN molecular transition in a molecular cloud. The linear effect can be seen in measure lines, for instance. Here it's just a compilation of some of the molecules that can emit for Zeeman at Alma frequencies. And these are the normal lines, so to say, are characterized by a strong Z, which is the so-called Bohr magneton. It's a magnetic property of the molecule. And these are observable at Alma frequencies, while these are the measure lines, also observable at Alma frequency. And here you see a result of an SIO maser linear polarization observed recently with Alma. Here you see the spectral variation of the Stokes, not I in black and Q and U in red and gray. So the last effect I'm going to talk about is the Goldreich-Kilafiz effect. It is probably the most difficult to observe because it's really a faint variation, but it's again due to the fact that the transition level gets split in sub-levels, but due to local anisotropies in the line optical depth or in radiation field, the population of the different transitions are non-balanced. So there are some transitions more populated than other, and the resulting polarization is always linear. Both it can be parallel or orthogonal to the magnetic field. So maybe this is not actually the right picture to show the Goldreich-Kilafiz effect, sorry. The measurements of this effect will provide the direction of magnetic field in the plane of the sky. And this is one of the first detections of this effect. As you can see, again, here you see the Stokes line, very bright, and the Q and U linearly polarized emission, where you see the level of the Stokes Q and U is very faint compared to the Stokes I. So this is a very subtle effect, which needs high sensitivity first and high calibration accuracy to be detected. So I'm going to finish with the last two slides, introducing the datasets that you are going to explore with Tobia. It's a very rich dataset. You will find in the archive both continuum and spectral lines observations in full polarization mode. There are 3 lines in the spectral range of observations, and this has been chosen. In particular, the 13CO and the C18O transition was expected to be a good candidate for a Goldreich-Kilafiz effect detection. Here, I just want to show the continuum emission observed in both sources. Sorry, I didn't say that the dataset contains 2 protoplanetary disks. And you see the Stokes and the linear polarization images for both sources, which are obtained from the continuum observation, and the origin of this polarization is not yet clear. Possibly is due to scattering, as I mentioned before. Here instead is a summary of the spectral line observations. Here you see the picture show the moment zero CO221 Stokes emission, which is really extended and very beautiful if you look at the channel images. But the actual lines where the Goldrake Kilafiz effect was expected didn't show any linear polarization. So there was no detection of the expected effect. Instead, in this same line, CO221, there is a marginal detection of Stokes Skew emission. Here you see in both panels the spectra, the Stokes spectra. The Stokes I is in black, and the colors are the Stokes Q, U, and V. Stokes V is mostly noise. And here you see that there's a tentative detection of the Stokes Q in Stokes Q in blue. But comparing with the Monte Carlo simulation, they decided that it's a marginal detection. What I wanted to remember to let you notice is that the Stokes I flux here is divided by 80 in order to have the lines in the same plot for all the Stokes. So just to emphasize again how faint the effect would be, how faint the level of this observation should go to be able to actually detect something. But please go go to the publication for more details. And then I think I stop here and hope you will enjoy the exploration with the new glasses you got.
My name's Tobias Karotsi from the Nordic ARC in Sweden, here in Uppsala. And I will give you a live demonstration of the full polarization Alma archive. And of course, people tend to shy away from polarization. They think it's a niche area, of course, and even sometimes you feel that it's a bit too complicated to do anything with. So the idea here is that we will try to give you using just the hands-on, just a simple demonstration that you can, to get hands-on familiarity with the full pole data. And we will use Carta, which you can access directly from the browser. And with this, we will hopefully sort of convince you that there's potential in the full polarization data and in the archive. And that in fact, with these modern tools nowadays, it's fairly easy to visualize and do basic analysis with almost no prior tools, really. Of course, I have to raise a warning here that because we're doing this we want to do this in real time and online. If everybody starts to follow along, we might stress the Alma archive a bit, but we've been reassured that this should be okay. They're claiming that we can do at least 100 people can access at the same time. But in any case, if we notice that there's a lag, you'll understand why, and we'll try to address that problem. So to do this demonstration, all you need is a browser, a modern browser, and the starting point will be to go to the Alma archive, which I'm assuming that you all are familiar with, how to find the link for that. And if we go to the Alma archive, we can see that there's lots of projects already here in the Alma archive. But if we want the full polarization data sets, we have to go to the search bar here. And all the way over here on the right, there's a field polarization type, which if we click on that, gives you the selection between single, dual, and full. So if we select the full, and we choose public data only, we see that the number of projects go all the way down to 150 about, and that's only not even 5%. So only 5% of the projects have full poll data. So it's a limited set. On the other hand, there's a lot of potential here, because if you look at the number of publications here, you will see that almost half of them are not published yet, or don't have a paper associated with them. So there's a lot of potential here. Now we've chosen a data set here that Rosita already mentioned slightly there. That's quite recent. We wanted to show a recent data set. So we select here on the max release date. If we click it in descending order and enlarge the view here, then we'll see that at the very top here, and released just recently a few months ago, half a year ago, we have one here called Measuring the Magnetic Field Morphologies in Disks Using the GK Effect, as Rosita was talking about. If we select that, we should get a dialog here that says that we can request a download. And if we then select that, we can request the download, and we're transported to the page to the Alma data request handler. I'll give it a few minutes to download. There, it's downloaded. Now, again, this is a recent data set because we wanted to show that because it has all the full polarization information that you can get out of Alma. If you go to previous cycles, you might not have things like these circular polarization, because it was only offered a few cycles ago. And so, yeah, so you just be aware that even though that I'm showing you a modern one, you might not find all the data products in the past, but in the future, at least, you will have all these data products available to you. So the view here is that the typical view, you have the raw visibilities, and you have auxiliary data, which is basically the QA, the quality assessment products. And then there's the actual data products. And we'll start with looking at the auxiliary, which is, again, the quality assurance, the QA things. And note, we'll try to pull up some things that are specific to the polarization data sets. So for instance, we have the weblog PDF, which is down here, which summarizes a lot of these other images that are in the auxiliary folder. And if we bring up the PDF, we will see the weblog, which contains most of the information that comes from the QA processing of the data. And for instance, I'll point out these things that are specific to the full poll data sets, which is the D terms. This is an image of the D terms, which, as Rosita was saying, you should look for low levels of D terms, which implies that the leakage between X and Y is minimal. And even though, of course, the calibration should handle this, you're still wanting to have as low as possible. And also, there's, I'll show you, you can see the fact that the effect of the polarization calibration going from the gain ratio RMS, going from high numbers to much lower numbers, the blue ones here showing after calibration, pole calibration, which gives you the feeling that the pole calibration was successfully mitigating for these instrumental polarizations. Another thing that you can look for in the data set, in the auxiliary data, is the script for imaging, which is a bit different for the polarization case. So for instance, it has a step 5 here, which produces products which are specific to the polarization data sets. And another thing to notice is that the T-cleans in the scripting, of course, have these IQs. The field for Stokes is set to IQUV, so you're getting all the Stokes parameters in the image. The images will contain all those 4 parameters. And here I'll show you the step 5 here, which is the calculation of these different products. So here you see the image math calls in CASA, which are specific to the polarization that calculate things like this capital P means the linear polarization, which is the sum of the Q and the U powers. And there's also this A, capital A, which is the polarization angle. And here you can play with things like the polarization threshold and the sigma levels, and to give you different visualizations of the data set, because this is quite tricky with polarization, that they're quite low levels of polarization, and the thresholding allows you to broaden or lessen the amount of image you see. So having seen those things that are particular in the auxiliary, the QA2 stuff, we move to the data products, and the data products that are specific. There's a lot of them, but it's to do with the fact that there's 4 sources here. 2 are science sources, the HD 1425 and the IM lupus source. And then there's 2 calibrators. One is the usual phase calibrator, but then there's something called the pole leak, which is specific to the polarization calibration done for full pole. And we'll start with that to show you how that looks like, and how you can. So we go to this pole leak and the multi-frequency synthesis with the IQU and the FITS file here. And you'll notice that on the right-hand side, there's these buttons which allow you to start a Carta session. And if we click on that, it will, after a brief pause, for it to start up, should bring up, yes, here we go. This is the Carta interface, which you can access with just the button click in the browser. Now the default image here is the Stokes eye here, which is the normal thing that you would see also without full pole data sets. And what you see is just the point-like source, and that's what you're expecting from a polarization calibrator. And now, of course, it's a pole calibrator, so there's got to be additional polarization information in here, and it's hidden away slightly in this tab called Animator. So if you click on the Animator, you open up a dialog here or a selection box, which allows you to select the different Stokes parameters. And it's done in the way that the components are numbered from 0, 1, 2, and 3. And the idea here is that they map onto, Stokes 0 amounts to Stokes I, which is the total intensity, which is the usual one that you always get with Alma. And then you can click here to get Stokes Q. That's component 1 is Stokes Q. Component 2 is Stokes U. And component 3 is Stokes V, the circular component. Now, if we go back to the Stokes I, you see, again, it's a point source. And if we select the Q, you see that there's Q there, and there's U, which is negative, which is the Q and the U are signed fluxes. So don't be afraid that it's negative. Whilst the Stokes V, which is the circular, as we were expecting, or as told by Rosita, these polarizers should be 0, and indeed it's showing us that there's no circular polarization. So that's good. Then we can go back and let's see some other, go to the actual target, science target, which is this HD 142527. We can do the same type of plot that we did for the polarization leakage. So we select the HD 142527, the MFS, the multi-frequency synthesis, the IQU, and the FITS file has a little Carta button, so which we can click. And that brings up, after a few seconds, the Carta image of the science target. And as Rosita showed already, this shows a nice disk region, which you can see here. And again, you can select in the animator, you can select the different Stokes components here, the Q and the U. And in this case, you go to the Stokes V and you see that there is something there. So it's interesting that you have some Stokes V there. There was this is again just the multi-frequency synthesis image. Let's go for the let's go and have a look at the cubes, which is even more information, of course. So we take again the same source, the HD 142527, go to the cubed one, and that's all the frequency, all the spectra, that spectral line information, and the IQU, and the manual, the polar. I should say something also about the fact that the PB core means that this is it's primary being corrected. But you've got to be aware of the fact that it means that it's the Stokes I which is corrected for, and the other components are actually not corrected for, and the calibration is only done on axis. So off axis you could get some distortions still, but they're in the limits that Rosita was talking about, that you should stay within those primary beam. So just to understand what it means for the polarization, that the PB core doesn't actually correct fully over the field of view for the primary beam. So we click on that and we bring up the Carta image of the spectra, and that should allow me to show you something else, namely. When we click on the animator here, we see that there's, of course, the channel information, besides the fact that we've already seen the Stokes parameters. So here you can play and look at different spectral components. And if we go to channel 24, we see a nice image here of this disk, and these two hotspots here. And what I wanted to show you in this view is when you have the spectral, the cube data, you can bring up a dialog, a widget called the Stokes analysis widget, which if you click on that, brings up this widget, which is specific to the polarization data. It has the QU stuff, and you fiddle with that. You can place that in here somewhere, pin it. The idea is you use this pin button to pin it into the, and you make some space for it, and you eventually get something that you might not have seen before, which is this plot of the linear components, the Q and the U, both as a spectra in these plots, and then there's the linear, total linear, so that's the square root sum of the Q and U in this plot, and then there's the polarization angle in this as a function of frequency, and then there's also this plot where you can see a scatter plot view of the Q and U plotted in Q and U space. So there's U on this axis and Q on this axis as a function of frequency. They're color coded in frequency. In this case, there's not much showing up. It's all scattered about. There is, in the case of a data set, which I'll switch to now just to show you, illustrate this. This is a case where you see the scatter plot showing a nice rotation of the Q and U with a function as a function of frequency. So it's going around in these circles here nicely, and this is indicative of Faraday rotation. So this plot can be very useful to look at that type of effect. And you can switch here between the scatter plot being in units of full power, or you can also click this button which says fractional polarization, and it gives you the plot in percentages. So you see that it's only a few percent polarized here, but still you can see a clear effect here on this region that I've marked out here. So that shows you how this Stokes widget, Stokes analysis widget, can allow you to look at the rotation of the field over frequency, which is a nice thing to be aware of. Okay, so let's go back to the data handling request list, and we'll have a look at the other products in the this list. And another one is the linear, the total linear power flux in which it has a little capital P in the name. And if we click on that, we'll get an image of eventually the total linear power, which has this nice looking disk here. And we'll also have a final look also at the this data product called capital A, which is the position angle, or also known as the EVPA. And if we click on the Carta button for it, and we will soon have an image here of the this is the polarization angle now. And what I wanted to show you here is the fact, okay, well, to understand this one, you have to remember that it's being thresholded here when we do the IMMath step to calculate the polarization angle, because there's potentially a lot of noise in there, and then you'll get vectors all over the place. What you typically do is you threshold on the total linear power so that you have some polarization there, and then you calculate the angle on it, so it's not just noise. And so that's why it looks like this, but it should be the same as where the linear polarization here is significant and is above the threshold. And then you get this image of the polarization angle. And what I should point out further is that what you can see is it looks like it's discontinuous. So it's jumping from plus 90 to minus 90 here. But in reality, as Rosita mentioned, this is an ambiguity in the polarization ellipse. You can't tell the difference between an ellipse that's rotated 180 degrees. It's the same ellipse. And so this jump in angle is actually not a real discontinuity, but just a mapping onto the angle here. So unfortunately, yeah, Carta doesn't handle this very well, because again, you would like to see this image as being continuous. So what you could do is you can switch color maps to make it look more continuous, but unfortunately there's not a good color map which wraps around on the edges. There's one called Seismic, which is a little bit more little bit more continuous, but still it still looks a bit not really that nice. But that's a limitation that they might add color maps. I'm not sure about adding color maps. There might be some way of adding your own color map, but I don't think so on the, at least on the browser version. Yeah, that's about what I wanted to say. I just finish off by saying that there are, of course, other sources that you can have a look at there in the data set. There's the I Am Lupus one. And I will finish off by saying that, well, I've hopefully shown you that it's easy to use. I didn't notice any latency or lagging in the database. And it was, all you needed was a browser. You could click on things that may be slightly hidden away, these polarization aspects, but you can find them fairly easily. And as I said, there's hundreds of public data sets already available, and a lot of it is not published. So there's a lot of potential here. And so I think with that, you can start going online and exploring the Alma polarization data set. Thank you.